Hi. So I was getting ready to start my lecture on the physics of nanoparticles, magnetic nanoparticles, and it occurred to me that maybe some of you could stand a review of some of the terms and concepts introduced in introductory physics, because it might have been a while ago. So that's what this is, a review of magnetism. So first of all, remember from your introductory physics course that current loops are what create magnetic fields. And in 3 dimensions, what will happen is the magnetic field lines around a little circular current loop will basically create a donut shape. The magnetic field will come up through the center of your coil and then kind of spiral outward and loop back on itself. And it does that in 3 dimensions. And if you were to look at it, it would look like a donut. So the magnetic field is strongest in the center of the loop, and it points perpendicular to the plane of the loop in the center, okay? So we're going to draw a vector pointing in the direction of the field at the center and call that vector the magnetic moment for the current loop. Now the formula that we'll get for this magnetic moment is equal to the current through the loop, I, times the cross-sectional area of the loop. So for a little circular current loop, it would be pi r squared, where r is the radius of your current loop, okay? And we're going to use mu as the symbol for the magnetic moment. So what happens is that in the presence of an external field, in other words, not one created by the current loop, but maybe a bigger, stronger field coming from somewhere else, okay, there's going to be a torque on that current loop. And that torque, tau, will be equal to the cross product of the magnetic moment with the external field, B. And in general, any current loop that has a magnetic field and thus a magnetic dipole moment, this includes atomic level current loops that are described in some models of the atom, specifically the Bohr model of the atom, which you learn about in modern physics. And this helps explain why materials exhibit magnetic properties. If you think of an electron orbit as a little tiny current loop, and then that electron orbit has a magnetic moment associated with it, then you can understand why an atom might rotate to align with an external magnetic field, or rotate in another direction as well. But anyway, there'll be a torque on that atom in the presence of an external magnetic field due to the little current loops made by the electron orbits, okay? The electrons in the atom have magnetic moments. So we're going to, because it's easiest to visualize from a semi-classical model of the atom, like the Bohr model of the atom, we're going to use this as our jumping off point. So remember, the Bohr model of the atom isn't 100% correct. There's things that Bohr got right and things that Bohr got wrong. But it is a nice conceptual tool for helping you visualize certain things. And like I said, it did get certain numbers correct, so it's still a useful pedagogical tool. So in the Bohr model of the atom, the electrons move in circular orbits like the planets do around the sun, okay? Now, it turns out that this is one of the big things that Bohr was wrong about. They don't move in circular orbits. They move in crazy orbits all over the place. And it's really just sort of a probability distribution about where those electrons are going to be at any given time. But for now, let's just use Bohr's simple conceptual tool of an electron moving in a circular orbit around the nucleus. Okay? So we're going to assume that the nucleus is at the center of this circular orbit, and that your electron is moving in the circle here, making a little tiny current loop. Now you're going to have a magnetic moment of that electron associated with the orbital motion. Okay, now remember, current is usually defined as the direction of positive charge motion, not negative, right? So that would mean that the current in this loop is actually flowing in the direction of the purple arrow here, okay, if the electron is moving in the opposite direction. And in that case, that would mean that our magnetic moment points downward in this case. Remember, you can figure out what direction your magnetic moment is going to do by using the right-hand rule. So if you take your hand and curl your fingers in the direction of current flow, then your thumb is the direction of the magnetic moment. Okay, so in this case, we have a current going this way, so our magnetic moment points down. Now, if you think about it, anything moving in a circular orbit will also have an angular momentum, described by the equation r cross p. Well, if you think of r as being the vector that points from the center of the circle to the position of the electron at any given time, and you think about the direction of the rotation of the electron as being described by this gray arrow here, then by a slightly different right-hand rule, you can see that r cross p gives you an angular momentum of the green arrow that points upward. So you can see here that your angular momentum and your magnetic moment point in opposite directions, and that's because it's a negative charge. If it were a positive charge, they point in the same direction. Now, this model assumes that the electron is moving with a constant speed v in a circular orbit of radius r, and so it's going to travel a distance of the circumference of that orbit, 2 pi r, in some time interval we'll call capital T, the period. In that case, the current associated with this orbiting electron, remember a current is defined as a charge divided by a time, so that would be the charge on an electron E divided by the period T, right? And then you could rewrite that using the equation that V is equal to 2 pi r over T as EV over 2 pi r for your current, okay? Now, that means that if you define your magnetic moment as the current times the cross-sectional area, then you can rewrite that as IA, and plugging in for the current that we had on the previous slide, I times A would give you 1/2 EVR, okay? Now, the magnetic moment can also be expressed in terms of the angular momentum if you want to do that. Remember that for a circular orbit, the angular momentum is mvr. So if you plug in then for an angular momentum, in terms of a magnetic moment, you would get E over 2m times L, where m is the mass of the electron. E is, of course, the electronic charge, which is 1.602 times 10 to the minus 19 coulombs. Now, getting back to the Bohr model of the atom, Bohr said that the electron orbits were at these quantized radii. And de Broglie later explained that is due to the wave nature of the electron, okay? So you get interference of the waves of the electron. It forms a standing wave then, and those standing waves can only occur at certain positions from, certain distances from the nucleus, and so those are your Bohr orbits, okay? And they also become known as the principal quantum number n, or the energy level of that orbit. So anyway, you only have certain orbits where these electrons can move through. And that means that the angular momentum and also the magnetic moment are going to be quantized, okay? And yet again, it's the wave nature of the electrons that causes the quantization of the orbits and the interference due to a standing wave established. And this is a concept that's covered in modern physics. Now, if you want to put some numbers to it, in the Bohr model of a hydrogen atom, the electron moves in these circular orbits and the ground state radius is 5.3 times 10 to the minus 11 meters, okay? And in the ground state, it's moving at a speed of approximately 2.2 times 10 to the 6 meters per second. So if I plug in, then that gives me I is equal to EV over 2 pi r, then I get a value of 0.00106 amps for the current. And then if I plug in for what the magnetic field at the center of a current loop is, and if you don't believe me that this is the right equation, you can always look it up, that's equal to mu naught I over 2r, where mu naught is the permeability of free space. It's a fundamental constant. I plug in for my current and my radius, and I get a magnetic field of 1.2 Tesla, which is a pretty large magnetic field, actually. Now, if you plug in for your equation for mu, you get mu is equal to I times A. And if you solve for the current, 0.00106 amps times pi times the radius, 5.3 times 10 to the minus 11 squared, then you get the magnetic moment for that orbit. And it's about 9.3 times 10 to the minus 24 amps meters squared. Or if you want to switch the units over, and I'll leave this as an exercise to you, amps meters squared is also joules per Tesla. This is a number that pops up so often that we have named it, and it's called the Bohr Magneton, okay? And it's usually written with mu with a little b subscript for Bohr. So this is named after Niels Bohr, who developed the Bohr model of the hydrogen atom. And often people refer to the magnetic moments of atoms in terms of multiples of the Bohr Magneton rather than writing out this extremely small number for you. Okay? So that's your Bohr Magneton. Now, that kind of explains where magnetic moments in atoms come from. Now, in the presence of an external magnetic field, the magnetic moments that are due to these little tiny current loops, what will happen is they'll turn anti-parallel to the field. And this is kind of similar to the idea of Lenz's law from introductory physics. Remember, Lenz's law says that things like to be as they are. So if you suddenly introduce an external magnetic field, your little current loop will kind of generate a current to oppose that new magnetic field. So it wants to oppose the change. So this is similar to the idea that in the presence of an external magnetic field, these little magnetic moments are going to rotate to turn anti-parallel to the field to oppose the change. This is known as diamagnetism, and it's a very weak repulsion, and it's easily overcome by other phenomena. So if there's anything else going on in the material, like it's a ferromagnet or even a paramagnet, magnetic material, which we'll get to in a minute, then the diamagnetism is so weak that it just goes away and it's dominated. But in atoms with full orbitals, this is the whole story, and the material is diamagnetic. Now, some examples of diamagnetic materials are elements like copper, gold, and silver, shown here in the image, okay? Okay, but there's other kinds of materials, and I'm going to move on now to the next kind, paramagnetic. But to explain that, I have to remind you of electron spin, okay? So, electrons and other particles as well have an intrinsic property called spin that also contributes to their magnetic moment. Now, it's important to realize that as far as we know, electrons really are sort of point particles, so to think about what it means for them to physically be spinning is kind of crazy, okay? I think of it like the electron has an intrinsic angular momentum, okay? And this intrinsic angular momentum, if it helps you to think of it as spinning on its axis, go for it, right? So if you want to do it that way, then you could think of it like the planet orbiting the sun. It has an angular momentum associated with going around the sun, and that's its orbital angular momentum, but it also has an angular momentum from spinning on its own axis, okay? And that you could call the spin angular momentum, if you like, okay? This is actually a relativistic effect. In order to explain electron spin, you really have to go to the Dirac equations for relativistic quantum mechanics. So there you go. The classical model of electron spin would be this electron spinning on its axis. Now, we know from experimental measurements that the magnitude of the spin angular momentum is √3/2 times h bar, where h bar is Planck's constant h divided by 2 pi. So Planck's constant is one of those fundamental constants of science, I guess, and the value of it is 6.626 times 10 to the minus 34 joule seconds in SI units. So fundamental. Now, the magnetic moment characteristically associated with the spin of an electron has a particular value, and that value has been measured experimentally as EH bar over 2 times the mass of an electron. Now, if you figure out what that value is, then you get your Bohr Magneton again, 9.3 times 10 to the minus 24 joules per Tesla. Okay, so that is the magnetic moment associated with the spin of an electron. So you can imagine that if you sum it up, you're going to have a total magnetic moment for an atom, and it's going to be the vector sum of the orbital angular momentum and magnetic moment, which we talked about earlier, and the spin magnetic moments. Now, if the electron orbitals are full, then basically everything kind of sums to 0 in terms of the vector sum, or very close to 0, and then you get a diamagnetic material, right? But if there's electron orbitals that are not full, okay, then the vector sum can be non-zero, and in those cases you get a paramagnetic material because the atom will have a net magnetic moment. Some of those are shown over here. Okay, you notice that these are multiples of the Bohr Magneton. Now, materials whose atoms have small net magnetic moments are paramagnetic materials. Each atom in this case has its own moment, but there's really no long-range order to it. So you could have an atom that has a net magnetic moment like this sitting next to one that has a direction like this, and it just all kind of sums to 0 over the whole material if you do the vector sum. Now, however, in the presence of a magnetic field, the individual magnetic moments of each atom are going to rotate to align with that field. They're not going to line up perfectly, okay, but they'll kind of rotate that way. And they won't line up perfectly due to a number of reasons, thermal effects being a big one. In other words, there's a lot of random motion associated with it, and so to get everything to agree and all line up with an external magnetic field It's not going to happen 100%. So you'll get a net rotation if you sum over the whole material, but it won't necessarily be a very big number, and that depends on a lot of factors. Kind of reminds you of politics, right? Sorry. Anyway, examples of paramagnetic materials include aluminum, tungsten, and platinum, among any others, and they're pictured here in all their shiny glory. Okay, next category, ferromagnets. These are the ones that we make permanent magnets out of. Now, these substances exhibit strong magnetic effects, and we call this ferromagnetism. Some examples of ferromagnetic materials include iron, cobalt, nickel, and then your rare earth elements that give you those really super strong magnets that you've probably played with and pinched your skin with if you put it on your hand. Now, these materials contain permanent atomic magnetic moments that tend to align parallel to each other, even in a weak external magnetic field. So what's going on inside of a ferromagnetic material? Well, they form what are called domains, okay? So what happens is, within a region of the material, the magnetic moments of each individual atom are kind of strong enough that they start to influence one another, and then they have a tendency to line up within a certain volume. And that volume in which they're aligned is called one domain. Now, however, you can have ferromagnetic materials that have a net magnetic moment of 0. In other words, you have one domain that's pointing this way and one domain that's pointing this way and one that points this way, and it all kind of sums to 0. But within that domain, there is a net magnetic moment. You can see an image of that taken with a special kind of microscopy that shows the direction of the magnetic moments here in this rare earth magnet section. Okay, so you can see the different shades of gray correspond to different directions of the magnetic field within that domain. Okay. So the magnetic moments in the domains are randomly aligned initially, say, for example, and the net magnetic moment is 0. But if you take that ferromagnetic material and place it in an external magnetic field, what will happen is the size of the domains that are aligned with that external magnetic field is going to grow. In other words, they're going to rotate due to that torque to align with that external field. And this results in a net magnetization direction for the material. If you place the material in a strong field, then the domains that aren't aligned with the field become very small, and then in those cases, even when you remove the external field, the material may retain a net magnetization in the direction of the original field. And this was noticed a long time ago. They noticed that some rocks picked up other rocks or repulsed or attracted other rocks. Ores like magnetite, for example, have a tendency to do this. Now, how do we quantify all these different types of magnetism and what they do in magnetic fields quantitatively? Well, here we go, all right? The volume average of the vector sum of the magnetic moments in a material is called its magnetization. So the magnetization is equal to 1 over the volume times the sum of all the little magnetic moments from all the atoms, all right? Now, if there's an external field, which I call here B naught, and it's applied to the material, then the magnetic field inside the material will be different due to the material's response to the applied field. In other words, the magnetic moments inside the field will be influenced because of the torque mu cross B on each of those individual magnetic moments, and they'll do something, okay? They'll do something. In that case, the magnetic field in the material will be different. So then we get the total field, B here, is equal to B naught plus the constant, the permeability of free space, which is mu naught, 4 pi times 10 to the minus 7, anyway, in SI units. And then that times the magnetization vector for the material. Now, more terms. We can do some manipulation of this to make it a little easier to deal with and give us a constant to spit out to sort of parameterize materials, all right? So here we have B is equal to B naught plus mu naught M. I already said that. Now, if I define a new vector called the magnetic field strength, H, and I say that it's equal to the external field B naught divided by the constant mu naught, then I can factor that mu naught out, okay? And instead of having B naught plus mu naught M, I can have mu naught times factor H plus M, all right? So now H is my external magnetic field strength. Now, really, the response of the material will be proportional to the magnetic field strength in some way. right? So if you apply a stronger field, you'll get a larger net magnetization effect out of the material. So that can be done by relating the magnetization M to the magnetic field strength via some constant chi, okay, which we'll call the magnetic susceptibility. So if the magnetization is equal to chi times H, the susceptibility times the magnetic field strength, then I can rewrite that whole equation as mu naught times H times 1 plus chi. Okay, so you can see that the total magnetic field will be greater or less than, right, the external magnetic field according to the magnetic susceptibility chi. Now this linear relationship, it holds very well for paramagnetic and diamagnetic materials, but it doesn't work so well for ferromagnetic materials, and we'll talk about why in just a second. If you look at this table that I borrowed from this nice Indian education online site referenced here, then you can see what these susceptibilities are for some common materials. So for example, for paramagnetic substances, your susceptibilities are small positive numbers. In general, aluminum, for example, is 2.3 times 10 to the minus 5, but it's positive. Whereas bismuth, which is a diamagnetic substance, is minus 1.66 times 10 to the minus 5. So what this means is, in that the presence of an external magnetic field, aluminum, if you look at what the magnetic field strength inside aluminum is, it'll be slightly larger, right? The magnetic field will be slightly larger in aluminum and slightly smaller inside of bismuth, okay? Now, ferromagnetic materials is a different story. In that case, you get a non-linear response to an applied external magnetic field. So see here, if you do something called a magnetization curve, in the magnetization curve, we're plotting the total magnetic field experienced inside the material versus the magnetic field strength was externally applied, which is plotted here on the x-axis, okay? Then you get this cool looking sort of S-shaped curve, that S shape, I don't know. So what happens is, let's say that you have an initially unmagnetized ferromagnetic material, and it starts here then at the origin. So there's no externally applied magnetic field, and there's no magnetic field net inside the material either, but it is a ferromagnetic material. Now you place it in an external magnetic field H, and you start to dial the strength of that field up. You could do this, for example, by placing it inside a coil of wire and turning the current up. All right, so here it starts off at the origin, but then you can see this very non-linear looking curve, and then you reach the limit of your power supply or whatever, and so the strongest that you can get your external magnetic field strength is this H value. So it stops there, okay? And the response inside the field leads you to point A for the total magnetic field in the material. And then you want to see what happens. You want to say, for example, you want to make a permanent magnet out of your ferromagnetic material, which initially has a net magnetic moment of 0, right? Well, what you can do then is you can turn your field, your externally applied field, off, right? And then what will happen is the magnetic field inside of the material will still be non-zero because you've made all those domains align kind of in a certain way. They might not line up perfectly, but they line up well enough that you still have a net magnetic field due to that material. Now, let's say that you then reverse the direction of the current and hence reverse the direction of the magnetic field. Well, for a while, your magnetic moments are still kind of aligned anti-parallel to the field, and it takes a little bit for them to rotate. So you're going to have to turn the field strength up, and then eventually you'll cross the 0 line here where the magnetic field inside the material is 0 because of the external field being in opposite direction to what's remaining of the aligned magnetic moments. But then if you keep going with it and keep turning your field strength up, eventually those magnetic moments will work their way around, and all the domains will have, if you sum over them, a net alignment parallel to the new direction of your external magnetic field. And then you could just keep going from there. So if you keep going from there, you get this S curve generated, and it's known as a magnetization curve or occasionally a hysteresis curve. All right, so that's the story with ferromagnets. You can't really talk about necessarily what the susceptibility of them is because the response is nonlinear, and it's going to change, that slope is going to change as you change your external magnetic field strength. Okay, so for this lecture, Of course, I didn't make up any of this. This is some old physics here. So credit where credit is due. I taught introductory calculus-based physics for 9 years or so, and I used this handy-dandy textbook for a lot of it, Surway and Jewett's Physics for Scientists and Engineers, published by Thomson Higher Education. I adapted a lot of those slides for this lecture, so credit where credit is due there. Also, I'd like to say I used some figures from hyperphysics and from that nice online Indian education site. So if you want a nice free online resource for further reading on this subject or any subject in introductory physics, then I recommend that you go there. So thank you, and I'll see you next time.